Welcome to the video on complex roots, de Moivre's theorem, and powers/roots of complex numbers. So first we'll talk about complex roots with real coefficients. So to find a complex root with a real coefficient, you find it the normal way you would with quadratics by using the quadratic formula. So your complex roots occur in pairs. So if a plus bi is a root, then you also have a minus bi as a root. So for our first example, we have find the roots of x squared plus 2x plus 6. So our a value here is 1. Our b value is 2. And our c value is 6. So we have our quadratic formula where x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So it's going to be negative 2 plus or minus the square root of 2 squared minus 4 times 1 times 6 over 2 times 1, which we can simplify that. It'll be negative 2 plus or minus the square root. 2 squared is 4 minus 4 times 1 times 6 is going to be 24 over 2, which is negative 2 plus or minus the square root of negative 20 over 2. So since we have a negative here, that means we have an imaginary number. So negative 2 plus or minus I square root 20 over 2. The square root of 20 is equal to 2 square root 5. So we have negative 2 plus or minus 2i square root 5 over 2. We can factor out a 2 from the numerator, so we have 2 times negative 1 plus or minus I square root 5 all over 2. We can cancel these 2's, so then we get negative 1 plus or minus I square root 5. So our roots would be negative 1 plus I times the square root of 5 and negative 1 minus I times the square root of 5. So those are our complex roots, and as you can see, it occurs in a pair with a plus and a minus, your imaginary portion. So here we have de Moivre's theorem. So when you raise a polar coordinate to an exponent, you raise r to that exponent and multiply the theta values by that exponent. And for that to be true, n must be a positive integer. So for z to the n, we raise our r to the n, and then we multiply our theta values by n. So then you can also have r to the n times cis n theta. So for example, we have 4 cis pi cubed. So to do that, we would cube our r value. So we'd have 4 cubed cis 3 times pi. So our 3 went here and here. So 4 cubed is 64 cis 3 pi. Then we have 2 times cosine 5 plus I sine 5 to the 5th. So that would be 2 to the 5th times cosine of 5 times 5 plus I times sine of 5 times 5. So 2 to the 5th is 32. So we have 32 times cosine 25 plus I sine 25. So now we have an IB practice question, which is no calculator. So it says if z equals 1 minus I, find z to the 10th. So if we wanted to do it without de Moivre's theorem, we would have to do 1 minus I times 1 minus I times 1 minus I 10 times, which would take a really long time. So what we'll do is we'll convert our 1 minus I into polar form and then do that to the 10th power using de Moivre's theorem. So our real component is 1, and our imaginary component is negative 1. So we could draw a triangle, 1, negative 1. So our theta is going to equal inverse tangent of negative 1 over 1. And our radius is equal to the square root of negative 1 squared plus 1 squared. So our theta value is the inverse tangent of -1, which is going to be at -pi/4 radians. And then our radius is going to equal the square root of 1 plus 1, which is the square root of 2. So in polar form, we have that z equals square root 2 cis -pi/4. So z to the 10th will equal the square root of 2 to the 10th cis 10 times -pi/4. So that will simplify to z to the 10th equals the square root of 2 to the 10th, which is 2 to the 5th, which is 32, cis 10 times -pi/4. This will become 5/2. So cis -5pi/2. So there's your answer for that. Now we can use de Moivre's theorem to find roots of complex numbers. So for a positive integer n, there are n roots that can be found with the following equation. So here's our equation. And once again, it uses polar form. And for this, we have all of our roots can be found by plugging in 0, 1, 2, 3, etc. up to n minus 1 for k. So we can find one root by plugging in 0, the next root by plugging in 1, and so on. So for this first example, r equals 4 and theta equals pi. So we have the nth root. So this is our n value, n equals 3. The third root of 4 times the cosine of theta, which is pi, plus 2 pi times k. So we'll start with k equaling 0. So 2 pi times 0 over n, which is 3, plus I times the sine of pi plus 2 pi times 0 over 3. So this would simplify to the cubed root of 4 times the cosine of pi over 3 plus I times the sine of pi over 3. So that's one of the roots. And we're going to go until k equals n minus 1. So until k equals 2. So that's when k equals 0. So next we have when k equals 1. And all we'll do is we'll change this to be a 1. So our numerator is going to be pi plus 2 pi. So it'll be 3 pi. So we'd have the cubed root of 4 times the cosine of pi plus 2 pi. So 3 pi over 3, which is just pi, plus I times the sine of pi. There's our second one. And our third one, we're going to plug in 2. So it's going to be a 2 now. So it's going to be pi plus 4 pi. So we'll have 5 pi over 3. So we have the cubed root of 4 times cosine 5 pi over 3 plus I sine of 5 pi over 3. So there are your 3 roots for your first example. So for our second example, we have the fourth root of 16 cosine of pi over 3 plus I sine pi over 3. So r equals 16. Theta is pi over 3. N is 4. And k, we're going to do it until we get to n minus 1, which is 3. So we're going to do 0, 1, 2, and 3. So we'll have the fourth root of 16 times the cosine of pi over 3 plus 2 pi times k, which our first k value is 0, over n, which is 4, plus I sine of the same thing. So pi over 3 plus 2 pi times 0 over 4. So our fourth root of 16 is 2. Then we have cosine of pi over 3 plus 0. So pi over 3 over 4. So that's going to be pi over 12. Plus I sine of the same thing. So there's our first root. For the second one, we'll plug in 1. So pi over 3 plus 2 pi will give us 7 pi over 3. And then divide that by 4, 7 pi over 12. So we'll have 2 cosine 7 pi over 12 plus I sine 7 pi over 12. Then we plug in 2. So it's going to be 2 times the cosine. And then we have pi over 3 plus 4 pi over 4. So that's going to be 13 pi over 3 over 4, which is 13 pi over 12. Plus I sine 13 pi over 12. And then finally, our fourth root will be 2 times the cosine, and we're plugging in 3. So it'll be the cosine of pi over 3 plus 6 pi, which will be 19 pi over 3, which when we divide that by 4 will be 19 pi over 12, plus I sine of 19 pi over 12. So these here are our 4 roots for this second one. So now we have IB practice question number 2, which says find 2 roots in Cartesian form to the equation z squared minus 2z plus 2 minus I equals 0. So our A value is 1, B is negative 2, and C is 2 minus I. So we're going to use the quadratic formula, x equals negative b plus or minus the square root b squared minus 4ac all over 2a. So x equals negative 2 plus or minus the square root of negative 2 squared minus 4 times 1 times 2 minus I all over 2 times 1. And in this case, we're not actually solving for x, we're solving for z. So negative 2 becomes positive 2 plus or minus negative 2 squared is 4 minus 4 times 2 minus I over 2 equals 2 plus or minus the square root of 4 minus 8 plus 4i over 2, which is 2 plus or minus the square root of negative 4 plus 4i over 2. So before we find our root, we can do some simplification. We have 2 plus or minus the square root of 4 times negative 1 plus I over 2. Our square root of 4 is equal to 2. So we have 2 plus or minus 2 square root negative 1 plus I over 2. So we can simplify by turning each of these 2's into 1 by dividing everything by 2. So this is 1 plus or minus the square root of negative 1 plus I. So we need to find the square root by using de Moivre's theorem for roots. So we need to convert this Cartesian form of this root into the polar form. So we have negative 1 plus I. So we have a triangle here where each side length is 1. So our theta value will equal the inverse tangent of 1 over 1. So the inverse tangent of 1, which is pi over 4. And our radius is the square root of 1 squared plus 1 squared. So the square root of 2. So our square root of negative 1 plus I in polar form is square root of 2 cis pi over 4. So for our de Moivre's roots, theta will be pi over 4. Our radius is the square root of 2. N is what root it is, and it's a square root, so 2. And k will be every value up to n minus 1. So 0 and 1. So we have the nth root of our radius. So we have the square root of the square root of 2 times the cosine of theta, so pi over 4, plus 2 pi times k, so we'll start with 0, over our n value, which is 2, plus I times the sine of the same thing. So pi over 4 plus 2 pi times 0 over 2. So our square root of the square root of 2 is our fourth root of 2 times the cosine of pi over 4 plus 2 pi times 0, so pi over 4 plus 0. So pi over 4 divided by 2, so pi over 8. And we'll have that whole cosine plus I times the sine of the same thing, so pi over 8. Now we'll do the same thing where k equals 1. So we'll have the fourth root of 2 times the cosine of pi over 4 plus 2 pi, which is 9 pi over 4, over 2 is 9 pi over 8, plus I times the sine of the same thing. So for each of these, we have our theta values and our radius values for converting it back to Cartesian. So theta for this first one's pi over 8, and the radius is the fourth root of 2. So our real component, our a value, is going to be the fourth root of 2 times the cosine of pi over 8. And our imaginary part, our b, is the fourth root of 2 times the sine of pi over 8. For the second one, theta is 9 pi over 8, and the radius is the fourth root of 2. So our a value is the fourth root of 2 times the cosine of 9 pi over 8. And our b value is the fourth root of 2 times the sine of 9 pi over 8. So to get our roots, we'll go back to our 1 plus or minus the square root of negative 1 plus I. The square root of negative 1 plus I equals the fourth root of 2 times the cosine of pi over 8 plus the fourth root of 2 times the sine of pi over 8 times I here. And it's also equal to the fourth root of 2 times the cosine of 9 pi over 8 plus I times the fourth root of 2 times the sine of 9 pi over 8. The cosine of 9 pi over 8 is just the negative cosine of pi over 8, and the sine of 9 pi over 8 is just the negative sine of pi over 8. So this is also equal to negative fourth root of 2 cosine pi over 8 minus I times the fourth root of 2 sine of pi over 8. So for our final answer, I'll write it up at the top. So we have 1 plus or minus the square root of negative 1 plus I. So we have 1 plus or minus the fourth root of 2 cosine of pi over 8 plus I times the fourth root of 2 sine of pi over 8. So that's 1 plus the fourth root of 2 cosine pi over 8 plus I fourth root of 2 sine pi over 8. And that's also 1 minus the fourth root of 2 cosine pi over 8 minus I times the fourth root of 2 sine of pi over 8. We could do the same thing with the second root we found, but that's going to be the same answer as these two because it's just the negative version of this. So our negative with the positive will give us this one, and then our negative with the negative will give us this one. So it'll be those same two answers. So those are the two roots to the equation. So here's our third IB practice question. It says, when z equals 2 times the cosine of theta plus I sine theta, prove that 1 over 2z squared plus the conjugate of 1 over 2z squared equals 1/4 cosine of 2 theta. So let's start by figuring out what 2z squared is. So 2z squared is 2 times cosine theta plus I sine theta squared. So that's 2 times 2 cosine theta plus 2I sine theta times itself. So times 2 cosine theta plus 2I sine theta. So that's going to equal 2 times 2 cosine theta times 2 cosine theta is 4 cosine squared theta. So that was this. And then we have 2 cosine theta times 2I sine theta is going to be plus 4I sine theta cosine theta. And then 2I sine theta times 2 cosine theta is going to give us another 4I sine theta cosine theta. And then we have 2I sine theta times 2I sine theta is going to be plus 4I squared sine squared theta. So these 4I times sine theta cosine theta can be combined to become 8I sine theta cosine theta. And then we have plus 4 cosine squared theta. And then this I squared is going to be a negative 1, so we have minus 4 sine squared of theta. For this next step, you're going to need to know your trig identities because we're going to be using 2 double angle formulas. So our cosine squared theta minus sine squared theta is equal to your cosine of 2 theta. We're going to use that, as well as 2 sine theta cosine theta equals sine of 2 theta. So we'll have 2 times, we have sine theta cosine theta here. We'll pull 2 from our 8 to get 4I, and then we have 2 sine theta cosine theta, so times sine of 2 theta. Plus, if we have cosine squared theta minus sine squared theta, it's cosine of 2 theta. So we'll have 4 times our cosine squared theta minus sine squared theta. We missed that, sorry. So it'll be 4 times our cosine of 2 theta. So now we'll distribute our 2. So we'll get 8I sine 2 theta plus 8 cosine 2 theta. So now we know that 2z squared equals that. So we have 1 over our 2z squared. So we'll write our real part first. So 8 cosine 2 theta plus 8I sine 2 theta plus our conjugate. So 1 over 8 cosine 2 theta minus 8I sine 2 theta. And we need to prove that that equals 1/4 cosine 2 theta. So to get the same denominator, we're going to multiply the denominators by each other. So the new numerator of the first one will be 8 cosine 2 theta minus 8I sine 2 theta. And then we'll add our new numerator of the second one, which would be the denominator of the first. So 8 cosine 2 theta plus 8I sine 2 theta. And that will be over our 8 cosine 2 theta plus 8I sine 2 theta times 8 cosine 2 theta minus 8I sine 2 theta. So in our numerator, our 8I sine 2 theta is going to cancel because we have plus and minus that. And then we have 8 cosine 2 theta plus 8 cosine 2 theta, which is 16 cosine 2 theta, over our new denominator. So we have 8 cosine 2 theta times itself. So we have 64 cosine squared 2 theta. Then we'll do our outside and inside values will cancel because we'll have a positive and negative. And when you multiply the conjugates together, those ones will always cancel. So then we'll just have our final value. So we'll have minus 64 I squared sine squared 2 theta. So if we factor out the 64 on the denominator, we get 16 cosine 2 theta over 64 times cosine squared 2 theta. And then this I squared is going to turn into a negative 1, so we have plus sine squared 2 theta. So for this, we'll need another trig identity. So our cosine squared theta plus sine squared theta always equals 1. So this whole part here will just become 1. So this simplifies to 16 cosine 2 theta over 64. We can divide the top and bottom by 16, and then we get 1/4 cosine 2 theta. So we've proved that this expression equals 1/4 cosine 2 theta. So in summary, we have some important equations. So for complex roots, they always occur in pairs. So if a plus bi is a root, then a minus bi is a root. Then we have de Moivre's theorem. When you raise a polar coordinate to a positive integer exponent, n, then you raise r to the exponent and multiply the theta values by the exponent. Finally, for de Moivre's theorem for finding roots, for a positive integer n, there are n roots that can be found with the following equation, and that's your equation there, where k is going to be all of your integers from 0 up until n minus 1. That's all for this video, and thank you for watching.